Alright, so Pourbaix diagram for nickel water system. Right, so in the previous discussion, we went through the process step by step, trying to find the the lines or the regions using equation 1 to 4. So we've done for this, we've done for this as well, we've done for this, and when we go to equation 4, we go to know that it doesn't depend on E or pH, right? So there was no line for it. So we are done with these. So now we continue from equation 5 to 8. All right. So after we did all this, we end up getting regions as this, and then this is what we have: nickel 2 plus here, and then we have Ni-O here, and then we have just solid nickel on this side, right? So we will continue build upon this to see what we get in the end, right? Solid. Okay. So now we move on to equation 5, right? So this is equation 5. So equation 5. Right. So for equation 5, we have H plus E minus, right? Let's go to H half, right? H2. Right. And then we know this clearly that this one is dependent on pH, and this as well dependent on the potential, right? All right. So then let's see. If we, meaning that we can use a Nernst equation, right? So let's see. So for Nernst equation, we have E ox, right? This is the format that we've been using, so we are going by that. What's E standard ox, right? Plus 0.059 on N. Very important, not 2. So don't get confused with that. So let me highlight N. So that in the end, you get to know, when you get to the number of electrons needed, you put it there, right? And then we have a log of reactants over product, right? Okay, there's a general equation. I'm just writing this so that we get to know what we are doing, right? Okay, so that's what we're looking for, oxide. Alright, so now we move on to the calculations. So it's always good that you're able, when you get the basic concept, knowing which equation to use at a particular time, and then what values to use, and then being able to read some values from a table makes your work easier, right? Faster, let's say that. So clearly, because this reference electrode, standard hydrogen electrode, we know the value for the standard E naught is 0, right? Here we have plus, and then we have we know the number of electrons involved is just 1, so we end up getting 0.059 log, right? So here what happens is that, let's see, let's take this down a bit. All right, so now we are going to write the reactant concentration of reactants and that of product, right? So for the reactants we have only H plus, right? And then for the products we have H, right? H2 to the power what, half, right? And then we've said that whenever we have something like this, what we do is that because we have a gas involved, we use pH instead of concentration. We've seen that, so that's plus 0. This goes to 0, so we have 0.059 log, right, concentration of H, right? And because we have a gas involved, let's rewrite it first. And here we have a partial pressure of what, H2, right? And then because of the conditions we are assuming, one of the conditions that we assume is that the partial pressure of gases, right, H2 partial pressure of O2 is equal to what, 1 atm. That's what we've already discussed, right? So we end up getting 0.059 log concentration of H plus. So we get this. And then another thing we notice that we've already drawn a relationship between log of concentration, right, of H plus, and then pH, where we've seen that log of concentration of H plus is equal to, some of these things I'll skip them the next time, but this is just for us to be able to follow. So we get this, right? So that will mean that we end up getting 0.059 0.059 times minus pH, right? And that ends up giving us minus 0.059 pH, right? And then we've seen that this particular equation depends on pH, right? And then potential as well. So this is what we have. Okay. So with this information, we should be able to draw a line. There's one other thing that's a little bit subtle but very important. When we look at the equation again, so there's the equation, right? Clearly, we see that there's some H plus there, and then we've seen based on some basic chemistry that we know that now we have this equation. This kind of shows that this reaction happens in acidic medium, right? And when we have OH minus this for basic medium, right? Yeah, so we've seen that. So this basically means that this happens in acidic medium, and that will mean that the range of pH that we can do for this particular one will be when the pH is less than 7, right? So this is the region where we'll be able to draw this line, right? The region where we'll be able to draw. With that information in mind, this is what we can do with that. Having the equation for the as in the E-oxide and then the pH, this is what we can do. We know that what will happen is that we'll be able to, let's see, draw the line for this particular equation, reaction equation, up to the 7, below 7. So let's say about 7, right? So let's just do the demarcation here. This is something that will have to go off later, right? So we know up to this line. And the next thing is that this is the equation that we have. And then the lowest value that we can get for this E-oxide for equation 5, right, is when the pH is 0, right? When the pH is 0. So when the pH is 0, we end up getting, let's see, everything to be 0, right? So then we have to draw a straight line, right? But then, because this is a straight line that we are drawing, we don't know where exactly. We need at least 2 points. It should be 2 points, right? So we need 2 points. One of them we know is 0, which is here. The next point we don't know, right? So definitely we know that it will be what do you call it? What's the name? A slanting line, right? Because the more you increase the value for the pH, right? The more you increase the value in this is the equation, right? So the more you increase the value for the pH, the lower the oxide becomes, or the potential becomes, right? So we know it's a downward line like this, something of this sort. We have something like this, right? Oh. So yeah, so we know we have something of this sort. So clearly it shows that it crosses this line somewhere, right? So remember that when we did the first part, when we started, we had a 0.2 minus 0.25 potential here, which was a straight line, right? So that would mean that it crosses that line. And then what it means is that we have to find the intersection of these two lines, be able to find the second point. We have to draw this first line that we are talking about, right? All right. So this is how we go about it. So the equation that we had was this. Let's see. We had this, right? pH. So we had this 0.059 minus 0.059 pH, right? Which is for this particular equation 5 we are talking about, right? And we said that because what do you call it? Decreasing slope line, it definitely crosses the line where we have the EH to be, that's horizontal line, to be minus 0.25, right? So with this, we should be able to find our, what's the name? The pH, right? Or the values, or the point where the line you're about to draw intersects that particular line, right? So let's see. That's the next thing we are doing. All right. So let's see. So now that we have this part is just a man side, so straightforward. Minus 0.059 pH, right? Which is what we are looking for, right? And then we have minus 0.25. We solve this, it gives us this, right? So that means that point of intersection, right, should be a pH value of this. So that means the pH that we are looking for should be 4.2. Let's do 4.73, right, which is approximately about 4, right? A pH of 4. So that would mean that that's the point of intersection for us to be able to draw a line, right? So let's do it this way. Let's see. So I mean we need here, right? We know that the line that we're about to draw will have to end with this, right? Which we've seen. and now we find intersection point, right? And we know the starting point, so intersection is here. So we have 2 points. We can draw that line, right? So this is what we do. We from here, from 0, oh, no, from the 0 to this. A minute, I'm just trying to choose a line. From the 0 to this, right? So 0 to this up to here, right? Yeah, we got to go. Oh, let's make it a bit straight. So from 0, right, passing through the intersection point which we just found. And note, this is not this is just for illustration purposes. It's not as accurate as the. So this is what we have. Okay, let's make it a bit different color. Oh, and then one thing we skipped was that we moved the line beyond what we are supposed to go. Right. Initially, we said that this moves up to 7, right? So it should go up to just there and nowhere else. Right. So these are the 2 points that we have. So, oh boy. So this and this. Let's make it short dashes so we can identify it later. Up to 7. So this way it ends, right? So now we've been able to draw the equation for that particular one, right? So let's see. So now we'll remove these, right? I'm taking this out because we're building on a diagram, right? So this is where it ends, right? For that particular one, right? So let's see. Meaning we are done with the equation 5, right? Now we move on to the next. So now we need equation 6, right? Equation 6 appears this way. We have a 2H₂O plus 2E minus equal to H2 plus 2OH. Right. So we know this depends on E, right? Let's use something else. You know this depends on E, so depends on potential, and as well depends on what's the name, pH, right? So now we move on with that. Okay. Yeah. So now let's try and use next equation to see what we get, right? So we have E. Oh, there's no standard. Oxford. We have the equation already, so we move through to it, right? And then the standard here, let me just write it. The E not here, which is the standard for this particular equation here, because there are a lot of instances where they are given, right? Because for a particular equation, the standard potential has already been calculated, right? So here we've already been given the value, so we use it, right? So we'll use it straightforward. The value that we have for that one, the value that I have for that is trying to read the values. So we have minus 0. I'm trying to read on the table. 0.827, right? That's what we have for that. And then we have plus 0.059. The number of electrons involved is 2. Right? So we have 2 already. So let's see. Okay. Right. So we have 2 for that. Log. So let's see. Log. And then now we are going to jump something. We know this is a reactant, right? But it's a pure liquid, so we take it out because the activity will be 1. So meaning that we have nothing at the top there. So meaning that it's basically 1. So let's put that there straight forward. We're not going to write the whole equation. At the base, we have H, right? And we know that for that one, the pH of it is 1. We assume the partial pressure to be 1, right? So that one is 1 as well. So we have 1. And then the only thing that we can see about talk about clearly is this, right? So we put that there. That means that we have concentration of OH minus, right, to the power 2. So this is what we have, right? Okay. Now we have this, we move on. When we get to here, the only thing that's a bit complex, or let's see, not so clear is this, right? So there's a relationship we have for that. We've already talked about in the previous discussion, right? Where we said that we have there's the water dissociation constant K, right? Where we have this, right? Let's use something else. Okay, let's use this. the water dissociation constant, right? Where we see that this Kw is when water splits, right, to this component. We have this OH minus concentration times H plus concentration should give us 10 to the power minus 14. Right, this is a relationship. So this is what we use, and then we put that in, right, for us to be able to get this, right, so we can get pH from it, right. So this is the relationship we are using. So let's see. Let's put this. Okay. All right. So we move on. So now that we've seen this, in that we have minus 0.827, right, plus 0.059 on 2, right, and here we have log, right? And then if we try to make this a bit simpler or clearer, we write it this way: concentration of OH minus to the power minus 2. We know that the concentration of OH minus is the same as 10 to the power minus 14, right, on concentration of H plus, right? So that's what we put in. So let's take this down as well. Okay, so this is what we get: minus 0.827 plus, when we simplify what we see above, 0.059 on 2, that's 5, 59 on 2. Because of this log that we're having here, right, we bring the 2, so we get times 2 times minus 2. Very important. We have minus here, right? So this, let's see something else. It's a minus here, right? So we get let's change this up, times minus 2 log concentration of OH, right? OH minus OH minus, right? So this is what we have, and then we know this takes care of this, but the minus is still there. Let's make it clear. This minus is still there, right? Okay. So now we put the substitute the OH for what we did, right? So we have minus 0.827, right? Here becomes minus, right? And we have 0.059, right? And then we have log the concentration of OH tends to 10 to the power minus 14, right, on concentration of H plus, right? Yeah, so this is what we have. So 0.827, right, minus, if you try to expand the log, so that's what we're trying to do here, right, expanding the log. So we have a minus 0.059 log, right, 10 to the power minus 14, right? And because of this division here, as we discussed, we end up getting another minus, right? So this is one, this another one, right? This is the other part of the log, 0.059 log concentration of H plus, right? And then we've seen the relation for that already, where we change it to pH, right? 0.059. So we get so we can simplify this side. So let's see what we have for that. This, let's simplify this side. So that means we have minus 0.827, right? Minus 0.059 log, that's mistake, of 10 to the power minus 14, right? Oh, trying to zoom in so we can see it there. Okay. So this is what we have, right? So this gives us a value to power 14, and this gives us a value of see. So we place all the minus, yeah. So this is the first minus we have. This one is here. We're just trying to confirm if we are on the right path. Because of this here becomes minus, right? So minus here as well. So minus 0.827 minus 0.059 is 10 to the power 14 minus 14. Yeah. So we're on the right part. So we have minus 0.001, right? Yeah, which is about 0, right? 0, about 0, right? So should we keep it? Let's keep it. We'll do the random later, right? Just for us to see what's happening. So now we've cleared all this to the minus 0.001, right? So this, we are on this part here. So minus, right? Here we have 0.059. Let's see, let's simplify this side. Right. Okay. Right. And then we have a log of pH, right? And we know the relationship already where we hit this will give us minus pH, right? So the equation that we get in the end, we know this to be approximately 0, right? So we get this goes to 0 and we get this negative here is cancelled by this. We end up getting just what's the name? Plus, right? Yeah, plus. So we get 0.059. There's a slight overlook, and so here must be negative, right? So let's go by it. We know that this negative 2 was brought about because of this. See, all these signs are very important. So we know that this negative 2 here was brought about because of this negative 2 here, right? So that's fine. So we have a negative here. And because of this division here, when we bring this one out, it should come with its own negative, right? So that negative will cancel this one here, take care of this, so we end up getting a plus at this side. So that will mean that we should get a plus here, right? And then when we change all of this here, right? When we change all of this here, right? Because we know the relationship between log concentration of pH, log concentration of H plus and pH, here is already a plus, right? Because of this, right? And this one comes with its own negative, so we end up getting a minus here. So in the end, we get minus 0.059 pH, right? It looks like the equation 5, but here's the difference. You see, for the equation 5, we said it happens in an acidic medium, right? And then here, clearly, we see some OH minus, right? If there's an OH minus, we know that occurs in the alkaline medium, right? Or basic medium. And because of this water here, basically what they say is that it happens in the neutral medium, right? So we see that a neutral or an alkaline medium, right? And because of that, we know that the pH will have a certain range, right? So the pH will be greater than 7, right? Because of this condition here, the OH minus that we have there. Right? So when we are drawing the line, we know how to go about it. Okay. So then again, we know that it's in line with this very first one, the equation 5 that we drew. But then the only difference we know, one thing we know about it is that it starts at 7, right? Start at 7. So if you have to draw a line for that, let's see. This is just for us to know where it starts from, right? So we know it has the same equation as the reaction equation 5, right? The only difference is that it happens in a neutral or alkaline medium, right? So as a result, we know that I start from here and it's in line with that one. So the only difference is that we just draw a straight line. That's a line that's in line with this green line that we have here, right? But then it starts from where the green line ends, right? So that's the only thing. So we're going to do that. I'm drawing a line that continues from where that one ended, right? Yeah, so that's it. But generally, when you see the actual what's the name, pubic diagram, it's just one color line, right? And here, this for the water stability line. We'll talk about that later, right? So these two together form what we call the hydrogen line, right? The hydrogen line. If you don't see water stability lines, there are two. The down one is what we call the hydrogen line. So now we have for equation 6 as well, right? Reaction equation 6. So now move on to 7. Right? So 7. So reaction equation 7, right? So what do we have for that? We have O2 plus, we have 4 H plus, then we have let's write this one. 4H plus, and then we have 4E. There's 4 electrons involved, and we have 2H2O, right? All right. So that's what we have. So clearly, if you are trying, this depends on potential and pH as well, right? Depends on potential and pH. So we can use this equation. When we are trying to do that, what we get is now that we know what the equation is already, we go straight for it, right? Then again, for this particular reaction here, the potential of such a reaction, so the standard potential for it is already established, right? And here we happen to have the value, or at times you are given a table to read from it, right? You have 1 point, so I'm trying to read from the table, 7, right? Right, so 2 to 7. So this is a standard potential. We have plus 0.059. How many electrons involved? 4. So it's not always you have to rush to writing 2 because you are familiar with the 2. Let me dip in that. When you get here, try and look at the equation again. How many electrons involved? You get that information, you move on. Right? Very important, else you will get a different value. So let's see. All right. So this is what we have. I'm just going to put the reactants, products. So let's see. We have log. So here we go straight forward. On the reactant side, we know the only one there is hydrogen, right? Hydrogen and oxygen, right? But then we know that this one here is a gas, right? So meaning that the partial pressure of air is 1, so we take that out, right? So let's do this first. It's 1, so it's still 1. We don't write it. And then for the H plus, right? So we put it there. H plus. And very important, this 4 here, very important, right? So we put that 4 here, right? And for the, what do you call it, the product side, we have just water. We know for that because we see pure water, so the activity of that is 1 as well, right? Yeah, so in the end we get this is the only thing we have, right? Just this. So we move on. So we have this, so let's see, we end up getting 1.277 plus 0.059 on 4. We change this whole log part to pH so we can get the equation we need to draw the line, right? So we get minus pH, right, to the power 4, right? First of all, let's simplify the log just to make sure things are not too messy. So we have times 4, right? And then we have minus pH, right? This is quite simple. So this takes care of this. So we get 1.277, right, plus 0.059 minus pH, right? Very important. The minuses are very important. Right? So in the end, we get 1.277, right, minus 0.059 pH, right? So this is what we have. And then looking at this one, we know it depends on, the reaction depends on the pH, and as well depends on E, right, on potential. So we know it's a diagonal line, right? Yeah. So to do that, that will mean that we have to be able to, what's the name? See, let's see. We should be able to do some things with it, right? But then there's something else we must look at, right? Then again, we've said that because of this H plus here, we know this one here occurs in, what's the name, acidic medium because of the H plus. So that will mean that has a limit. It happens up until, what's the name, 7, right? So we know that this line, which is equation, reaction equation 7, was in acidic medium, has a pH less than 7. So that will be the limit for it, right? But then we will have to find an intersection, right? But another thing we do is that we know is the least value that we can get for this particular one is when pH is 0. So we need to get 2 points. So that's 1 point we have. So 1.277, right? And then we have minus 0.059, right? And the lowest pH that we can get, the lowest value we can put there to get the lowest value for this is 0, right? So when we put 0 in, this is what we get. 1.277, right? Yeah, so let's see. Well, let's find that on the diagram. So this, you know, every small dot is 0.25, right? So you have one here. You have one. This is 1.25. So approximately it's just a bit above it, right? So it can be about here. Yeah, so that's the point that we've chosen. So now we choose a different color for this as well. Let's choose this. So it's clear what we are doing. So we have about here. So we have one point for it. And because we know it's a decreasing line, so there's the equation for it. Where is it? Right. So as the pH changes, right? As the pH changes, the value for this oxide will be changing as well. So the value for this oxide will be changing as well, right? Okay. And then it will have a, what's it called? It has a negative slope, right? It has a negative slope. And because of that, we know that somehow it will end up crossing this line again. So this line is very important in our discussion. This original line that we drew, right? For the first equation, reaction equation that we have. So we know at some point it crosses this line. That we know for sure, but we don't know where. So that's where we equate some things and find the intersection point, right? So that will mean that we equate all this to minus 0.25, right? So let's see. Equating them, we have 1.2. Oh, yeah, there's something missing here. This value here, reading it from the table, it was actually 2.2. So this was an oversight. Yeah, 2.2, we have it here. This is 1.227. This 1.227 as well. 1.227, right? 0.227 minus 3.059 pH, right? And we are equating that to minus 0.25. Let's see the pH that we get for that. Function that 1.227 minus 0.059 pH x here minus 0.25, and that gives us a pH of about 25, right? So which is not possible, but for the sake of our graphing is what we are doing that way, right? pH is about 25. Okay, so that will mean that we have 2 points when pH is 0, right? In this case, when pH is 0 here, we're not getting 1.227, right? 1.227, and on this here, so let's see, 1.227. How do we get that point? So we know the small demarcation is 0.25, so this is 1.25. So 1.227 is about here, right? I think we marked that already. 1.227. The next point we need is that we know this particular reaction. Looking at it, reaction equation 7, right? So we know it happens in a acidic medium because of this H here, right? So because of that, this is what we get, right? So let's see. Okay, it's 1.227. We have that, and the other is let's see. We know it will be a slanting line, right? Because of this minus here to have a negative slope, and because to have a negative slope, we know that to somehow end up crossing one line, which is this first line I will draw here from the first reaction equation. This. So we know it crosses this, but we don't know where. So our business right now is to be able to find where it crosses it. Right? To do that, that's where we've done the intersection. We know we've seen that it's the 25, approximately 25 there. But then on our pH scale, we don't have 25. So we know that to get to 25, we need to add about 9 to the 16 here, right? So this to the 16 here, which I know is about from here to about here, right? So I need a line that long to join to that one, get the endpoint for that, right? So just going to do something that's from here, just so we can follow what's happening, right? So let's see. If I join that line to this, I will see where my endpoint is, but maybe you won't. But let's see. Maybe it won't show on this screen though, but I'll be able to see where it ends. So basically, it ends about just the end here, right? So now we know where that is. So I have this point here, and then the next point is about here, right? Where you see this arrow, right? That's what we found. So now we know that this reaction, right, is in what's the name? Acidic medium, right? We know it's an acidic medium, so that helps us to establish another boundary, right? So let's check it again. Question 7, yeah, it's in H, so we know that happens in acidic medium, right? So if it happens in acidic medium, clearly we know that it doesn't extend beyond the 7 pH, right? It doesn't extend beyond that. So let's see. Let's draw the 7 pH first, right? So we know that's about here. Yeah. So now we have to find the intersection. We have to draw the straight line. So let's see. So we know that to know the beginning and the end, right? But we know the 2 point. We know the 2 point we need, right? So I'm tracing from what we have, that 25 that we have, to this 1.27, right? So that's trying to draw a straight line, right? Minutes. Okay. So let's see. Let's see where I get in for this. Okay. Okay. Because I see where that the point ends, I'm able to draw the straight line for that particular one, right? Maybe it might not be visible on the screen, but I know the end point and the starting point, right? So about here, and I know it joined this line here, right? Yeah. So join that there. So now we have where it ends and where it begins. Okay. All right. So that's it, right? And the next one that so now we are done with equation reaction equation 7, right? So we're going to reaction equation 8. 8 we know depends on E, depends on pH, right? Okay. So now we're using this equation, box red. And the standard for this one, given the red from table, I'm reading from the table, is 401, right? And then we have plus 0.059. Slowly I read the number of electrons are 4 log and then the reactants all are 1 the product have concentration of OH minus to the power 4, so this gives me 0.401 plus 0.05914, right, times, I'm going straight for it, times minus 4, and I have log concentration of OH minus, so this gives, so now that we understand the causation, I'm just going to go straight forward to it. 0.401, 0.059, here becomes minus, then I have log 10 to the power minus 14 on H plus concentration. So simplifying this, get 2.401, it's minus 0.059 log is 10 of 10 to the power minus 14. So this gives me 1.227, just that side. So what I'll be having for the rest is minus 0.059, right, log concentration of H plus. This comes with a minus at the top, right? So this minus takes care of this, and I get 1.227 plus 0.059. This here gives me minus pH, right? So I end up with 1.227 minus 0.059 pH, right? So this is what I have for equation reaction 8 as well, right? So looking at it, very similar to reaction 7. The only difference is that, as we've seen here, we have OH, right? So that will mean that the pH, right, greater than 7, right? So it continues from where reaction 7's line ends, right? So let's see how that will be. So this is what we are going to get. Let's see. Continue from there. We have this. Trying to draw a line for reaction equation 8, right? Yeah. Then again, this is freehand, so it might not be as accurate as the original. So now that we know this is the water stability lines, right? The top one is what we call the oxygen line, right? So if you don't see them when you see this, they are the same. And then the down one is the hydrogen line, right? Yeah. And there are reasons for that. When the water, we're not going to go into it. When the water splits below one particular line, produces hydrogen, above another one produces oxygen, right? Another question you might be having is that why is it that after going through all this, we are having a different diagram, similar but not completely the same as this one here? And the reason is that to be able to draw this one that we see here, you need a lot of reactions, right? A lot of reactions, right? Reaction equation. But here's the case that we're only given 8. That's why we ended up with this, right? So they are basically the same. And remember, this is freehand, so that's why we see some other regions like this and this, because a lot of other reaction equations have been used to derive the other lines, right? But then there's the basic one. You can build upon this if you have the other ones and get this one here, right? And then the other concern was that why is it that we use NiO when in the reactions we're seeing NiOH2, right? They are basically the same, right? Just that one is hydrated, one is dehydrated, right? Yeah. So as you can see in this particular one here, they are the same. So that's why it says this or slash this. All right, so that's it.